We're gonna go over a lesson 2.6 today, and it pertains to freely falling objects. Okay, so freely falling objects, well, their acceleration is constant, and is constant, and we actually call that acceleration as acceleration due to gravity, which is denoted by g. But remember, g is not gravity, okay? But the complete name for that particular symbol, for that particular constant, is acceleration due to gravity. So when an object is dropped near the Earth surface, its velocity is not constant. Okay, it accelerates downward at a constant rate of 9.8 meters per second squared, and again the direction is downward. And of course, in this particular case, we assume that air resistance is negligible. So that means that uh, gravity is the only one that is acting on the object. So it's downward. Uh, whether you're throwing the object upward or downward, the acceleration will always be negative 9.8. Again, in this particular case, we use the coordinate system that going up is positive and downward is negative, okay? So that we can say that acceleration is always negative 9.8 or 9.8 downward.
I have a
Yeah,
question. Where did
yes.
you get the 9.8 from?
Well, that should be later on. I don't know if we will be talking about uh, like Newton's gravitational law. Actually, you can get the value of g there. As long as it is near the surface of the Earth, the value is around 9.8. Okay.
Okay.
So we can actually verify that one in an experiment, and we will be doing that experiment next meeting. Let's see how close can we get to that particular value. Although essentially, if I think it's part of physics 12, the gravitational law of Newton, uh, essentially you can see in that particular expression that the value of g is not necessarily constant. It's actually dependent on elevation. So let's say, for example, if you're going to compare the acceleration due to gravity here, like in downtown Vancouver, and you try to compare it with the acceleration due to gravity in Whistler or maybe Mount Seymour, you should get a slight difference. Not necessarily that big, but there should be a difference in the value of g.
But
But
gravity would be stronger or would it be stronger on a mountain than it is here?
uh, no, actually, as you go higher, g would decrease.
Okay.
Yeah, because it's inversely proportional to the square of the distance. Like the
Sorry.
farther you are from the surface of the Earth, that's why as you move up, gravity is less and less and less, becomes lesser.
Okay.
So, yep. But there should just be slight difference. But then again, this is at least at the surface of the Earth. Well, the value of g is around this value, 9.8. Uh, Again, it differs with location though. Like strictly speaking, it should differ because of its dependence on the distance from the center of the Earth. Okay. So this acceleration is always constant near the Earth's surface. So this is some of the assumption. We're talking about just near the Earth's surface. So even if objects are thrown up or down, the acceleration is still constant. If you're wondering why is it that if I'm throwing the object up, the acceleration is negative, well, you have to remember that if you're throwing it upward, uh, the magnitude of the velocity decreases, even though that's a positive direction. So it decreasing, so therefore the acceleration is negative. At the same time, if you are throwing the object downward, it must be taken into account that, well, the magnitude of the velocity increases, but since the velocity becomes more and more negative, so delta v there is negative also. So you have a negative acceleration. Okay, so in both cases, throwing upward is negative acceleration as well as you are throwing it downward. Okay, so it was Galileo who actually first investigate this one mathematically. So if you have heard about the Leaning Tower of Pisa, that is considered as the first laboratory. So according to legends, Galileo Galilei tried to throw some objects there. Although he also like used inclines to investigate the effects, and he found out that, well, the value of g is just constant. And for the rest, in our case, we will use the value of g as negative 9.8. We'll just use that one. Although other books uses 9.81, let's just use this one here, negative 9.8 meters per second. Again, the acceleration is always directed downward, so it's negative. The negative sign there indicates that the acceleration is always downward. Any object in free fall, when we say in free fall, there should be no external force or external forces. No external force or external forces will accelerate at negative 9.8. Velocity does not affect this number. So that means that the initial velocity. Okay. One more thing about to take note if we're talking about free fall is that the initial velocity of the object could have three different signs. Positive uh, if you are throwing it upward. It's negative if you are throwing it downward. And lastly, you have zero velocity if, well, the usual term would be if it is dropped. Okay, so the initial velocity, try to take note of that because of uh, the coordinate system that we're using, this one here. So that means that if you're throwing it upward, it should be positive. If you are throwing it downward, that should be negative. And then if you're just dropping the object, that means that the initial velocity is zero. Well, this is helpful later on if you're dealing with freely falling object. Okay, so an iPod is dropped from the top of a school 10 meters and determine its velocity when it smashes the ground. Okay, so uh, it's always good to start any problem with a diagram. Okay, So the height of the building is 10 meters. Okay. So you have a person here tries to drop the iPod. Okay. Let's say, for example, in our coordinate system, as I mentioned, in the displacement equations that we have, displacement is the change in position. And if you have change in position, you're always talking about final and the initial. So it is much simpler if you're gonna make your starting point as the 0 mark. So that means that if this is 0 meter here, what do you think would be the position at the bottom? Is it not that at the bottom part, this should be negative 10.0 meter? Okay. So if you started at the top, the height, again, the height just tells you the distance between the topmost of the building and the floor, or from the ground going up. It doesn't matter. But if you're talking about position, that means that if this is initial position at 0, and remember that we try to use the coordinate system uh, above. Again, going up is positive, going down is negative. So therefore, the position at the bottom is negative 10. Okay? So determine its velocity when it smashes the ground. So to write the given quantities, well, it is being dropped. So that means that my VI is 0. Again, that word, automatically VI is 0. Then this is just a freely falling object. You're just being dropped. So try to assume that there's no air resistance. Okay. So therefore, the acceleration is just negative 9.8 meters per second squared. Okay. And we have delta D, in this case, 0 to negative 10 is just negative 10, or, well, in our displacement equation, we just use the symbol there, D. So we just use the simple D in this case. So this is negative 10.0 meters. And we want to solve for the final velocity. Okay. So now, what are the equations that we can use here? Well, in our discussion on 2.4, those are displacement equations, and displacement equations are applicable if the acceleration is constant. Well, freely falling object, acceleration is constant, so therefore we can use those equations. And examining the things that we have and the things that we don't have, in this particular case, we're not given the time. So of those displacement equations, there's only one equation there that doesn't contain time. So it must be, I'll be using that equation, which is Vf squared minus Vi squared plus 2AD. And then I'm just gonna replace my, this is 0 squared plus 2 times 9.8, negative 9.8 times negative 10. Okay. And Vf squared is equal to 196. And to get the Vf, I'm gonna take the square root of both sides. And according to the square root principle, again, there should be two roots. Vf is a plus or a minus 14.0 meters per second meters per second. However, if you can see here, it smashes the ground. So what is the direction that? The direction of that is negative. So therefore you choose the negative. So your VF should be negative 14.0 meters per second. Or again, the final answer, negative doesn't constitute direction, but it helps you in which to identify the direction. So you know that since in your coordinate system, negative symbol means down, so therefore its direction is downward or down. Okay. Even though I have two roots for my from the equation that I have, but then again, from the for this particular situation, obviously before it hits the ground. And one more thing, that's the thing that I want to emphasize. For this type of question, take this one as just before it hits the ground. Because you might be thinking, oh, when it hits the ground, well, it's at rest, so it's zero. Then again, it's just, it's the same thing as asking for the impact velocity. So the velocity just before it hits the ground. So maybe at the brink of hitting the ground. Okay, pod is thrown downwards. Well, he has a lot of iPod. Thrown downwards at 4.5 meters per second. What will be its velocity when it smashes into the ground? How long will it take for it to hit the ground? 4.2 seconds. I think there's a correction for this one. Let's just say, yeah, I think 4.5 meters downward. That is quite fast for a short height. Instead of downwards, let's say, just change it to upward. Okay, upwards. What will be its velocity when it smashes into the ground? So what you can do here, again, I'm just going to take note all the given quantities. Initial velocity is thrown upward, so that's positive meters per second. And then acceleration, again, this is once it leaves your hand, there's no other forces acting on that particular object. It's just acted upon by the force of gravity. So it is now in free fall. So that's negative 9.8 meters per second squared. And then again, displacement is negative 10.0 meter. So the question is just asking for letter A, what would be the velocity, so VF, when it smashes into the ground? Okay, so when you try to do that, again, we don't have the time component, so it must be the formula of VF squared plus VI squared plus 2AD. So this is 4.5 squared plus 2 times negative 9.8, so negative 10.0. So VF squared is around 216. And again, we just try to take the square root of both sides. But then again, I know that this is downward, so that's 14.7 meters per second, or it should be 14.7 meters per second down. Okay, it should be downward because when it's moving again before it hits the ground, it should be moving downward. So the direction is down. The negative sign there indicates that it's moving down. Okay, for letter B, it is asking for how long. How long will it take to hit the ground? So that pertains to time. Okay. Well, in this particular case, you now have an additional information. That means that your final velocity is already given, or at least you determine that one as 14.7 meters per second. Again, this is, you solve for this. Okay. So you have an additional information upon which you can use in order for you to solve for the time. So if you're gonna examine again your displacement equations, you can find there that everything is given except for the time, and it is given by this expression here. Okay, so therefore I can solve like this is negative 10 is equal to for negative 14 negative 14.7 and plus 4.5 and divided by 2 times time. Okay, this is negative 10, and then that's 14.7 4.5 divided by 2. That should give me 5.10 negative t. Solving for time, I will divide both sides by negative 5.10, 5.10. So that gives me 10 divided by 5.1. That should be around t is equal to 1.96 seconds.